Don't forget to subscribe and ring that bell.
Hi, how you doing? Glad you're here because we are going to do free response question number 5 from the practice 2018 AP Calculus AB exam that College Board put out for us to, well, practice, okay? We do not get a calculator for this problem, but you know what? Keep it. I don't need it. I got this. And you know what? So do you. Let's start free response question number 5 right now. First of all, let me start by saying, if you haven't seen any of the previous videos I've put up, I love graphs and tables and charts. They're the best. And they start by giving us this beautiful image, the graph of f. Number 5 reads, the graph of the continuous function f consisting of 3 line segments and a semicircle is shown above. Let g be the function given by g of x equals the integration from -2 to x of f of t dt. Find g of -6 and find g of 3. First of all, anytime I see something like this, I know at some point I'm probably going to have to find the derivative of g, which means I'm going to take the derivative of the integral, which will make it go away. I guarantee we're going to have to do that at some point. And you know what? I love doing that because it's simple. But for right now, let's focus on what A is asking us to do. Find g of -6 and g of 3. So let me start by getting my calligraphy pen. Let's go green. Okay, let's find g of -6. All right, and I will start down here. G of -6 simply means I'm going to throw a -6 into any x, which happens to be the upper bound here. So the integration from -2 to x, which is now -6, of f of t dt. Now this is wonderful because integration is the same thing as area under the curve. And what makes this even better is that my curves or my functions are straight lines and semicircles, so I can just use areas of shapes, triangles, circles, and whatnot. That'll be nice. But the first thing I notice here, if you have not yet, the first thing I notice is my bounds. The lower bound is actually larger. It's a bigger value than the upper bound. So I'm going to go ahead and switch those, okay? I'm going to put my -2, which is a larger value than -6, of f of t dt. However, when I switch those bounds, I have to negate my overall value. So I'm going to figure out what it is and just negate it at the end. All right, so let's go up to our graph, and let's see from -2 to -6. Oh, from -2 to -6. So it's really just the area of this triangle. That's a really easy. I can't believe this is like a geometry question. I can't believe it's an AP calculus question. But let's find the area of this triangle. Okay. The area of a triangle is 1/2 base times height. My base goes from -6 to 2. That's 4. That's a value of 4. So it's 1/2 of 4 times my height. Well, it looks like I go up to here, which is 5. Well, it tells you 5. So the height is 5. 4 times 5 is 20. Half of 20 is 10. Now, let's be careful here, because the only thing that they're really testing you on in a calculus manner as well, you need to know area under the curve is the same thing as the integral. But you also need to know your rules for integrals and their bounds. By flipping our bounds, I have to negate my answer. So my answer isn't 10. This part is 10. But don't forget, I have to negate that. So my answer is actually -10. All right? And that's g of -6. But we're not done. We need to still find G of 3. So let's go, ooh, I use all my little fancy colors. Orange. Okay, G of 3. I'm going to put this down here. And it's the same thing as G of negative 6. Okay, let's get a little bit more room here. I still need to put my value into my x value, okay, in my equation or function. So it's the integral from negative 2 to x. Well, my x is now 3 of f of t dt. And we've already established that we're still looking for area under the curve. This time it's going to go from negative 2 to 3. All right, so let's go back up to our graph. All right, and if you don't mind, I'm going to erase this and clean this up a little bit. And this time, I'm going to go from negative 2 to 3. Okay, so from this area to this area. So that big triangle, I don't need this anymore. That's this guy, I don't need this. I need the area of the semicircle. And then I need the area of this kind of small triangle here. Now be careful. Whenever I take the integral of something, any area that's above the x-axis is considered a positive value. This is my x-axis. Anything that's below the x-axis is considered negative. So the area of that little small triangle is going to be a negative value that I need to combine with the area of my semicircle, yes, semicircle, which is a positive value. Now you might be asking yourself, well, Visca, we did this and we got a negative. That's 10, that area. The only reason it was negative is because, remember, we had to flip our bounds. Okay? So let's go ahead and start figuring out our area under the curve from negative 2 to 3. All right? Again, I'm going to just get, let's clean this up a little bit so it's a little bit nicer to look at. Get rid of that arrow, this arrow. Don't need any of this. Get rid of that. And you know what? We really don't even need these. Let's make it a lot easier. Let's go. I'm a visual guy. I like visuals. I'm a visual man. Okay, here you go. That area should be positive, and the area of this little triangle is going to end up being negative. All right? Let's go ahead. Get our calligraphy pen, which I love. Man, I love the calligraphy pen. We'll go gray here. Okay. The area of my circle, area, it's pi r squared. I need to figure out the radius. Well, if I start at the origin, the radius is 2. That's a distance of 2. So it's pi 2 to my radius squared. So it really is just 4 pi. All right, that's the area of my circle. It's positive because it's above the x-axis. Right? Now let's think about our triangle here. And let's go, yeah. You know what? Let's go here, then go a light purple, though. I'm going to get a custom color. That lavender is nice. Okay, let's use that. Oh, that's pretty. So this triangle, again, the area of my triangle is 1/2 base times height. So it's 1/2. My base is 1. That base of the triangle is 1. And the height, this distance from here to here, is actually 2. It tells you it moves down 2. So it's 2. All right, and I'm looking at my work, and I know there's one thing we haven't done yet. So if you're like, you made a mistake, don't worry. We're coming back to it. All right? If you haven't caught it, you will, I don't know, not be shocked, but you're going to be one of those, oh, that's right. Anyways, the area of our triangle, 1 times 2 is 2, 1/2 of 2 is 1. So the area of the triangle is 1, but since it's below the x-axis, it should be -1. So a lot of you might be saying to yourself, good, this is good. This should be 4 pi for my circle minus 1 for my triangle. But guess what? This is not 4. It's 2 pi minus 1. Did you catch it or not? If I go back up here, and we'll go back to gray. Yep, okay. All right, it's frozen for a second. There you go. Come on. Gray. Area of a circle. This is correct, but don't we only have half of a circle? We only have half of this area. So really, I have half of my area of a circle, which means I need to multiply this times a half. Half of 4 is 2 pi. Don't fall into that mistake, all right? So I'm going to scroll back down here. That's why this is 2 pi minus 1, okay? So g of 3 is 2 pi minus 1, and g of negative 6, well, that's negative 10. Not a bad problem to start with. 5b. Find g prime of 0. And there it is. We're finding the derivative of g. But I love it. I absolutely love it. I'll go here. We'll start with black. Okay, and I've copied a shot of the graph because it's always helpful. All right. So first of all, we know g of x. That's the integration from negative 2 to x of f of t dt. Don't forget that dummy variable. All right, well, I don't want to find anything with g. I want to find something for g prime. So in order to find g prime of x, I need to take the derivative of this. And if I take the derivative of the left side, I also need to take the derivative of the right side. Now, the beautiful thing with derivatives and integrals, you can kind of think of them as opposites, right? They cancel. So the derivative cancels the integral, which means the dummy variable, which we love, goes bye-bye. Whatever's up here will replace the variable in here. So it's really f of x. Now, the chain rule applies here. I'm also supposed to multiply by the derivative of whatever the upper bound is. That happens to be 1. So I can do times 1, but, you know, we really don't need to multiply anything times 1 because it's itself when we're done. So the derivative of g is f. And we have the graph of f, which guess what? Isn't f the derivative of g? So as we're looking at the graph of f, we're also looking at the graph of the derivative of g. So when I say, now, what's g prime of 0, that's really saying, well, what's f of 0? And remember, train your brain. This is a coordinate. When x is 0, what's your y? We just need to find the y coordinate when x is 0. Okay, well, highlighter. X is, oh, it's 0 right here. So what's the y value of this coordinate right here? When x is 0, y is 2. That was simple. I love it. Love it when they give us things like that. 5c. Find all values of x on the open interval from negative 6 to 3, for which the graph of g has a horizontal tangent. Determine whether g has a local maximum, a local minimum, or neither at each of these values. Justify your answers. We can show math work or we can write a little note, any type of justification. All right, let's begin. Go here, blue. Here we go. So let's kind of break this apart, what they're asking us. Find values between negative 6 and 3. Okay, that's, well, negative 6 is here. 3 is here, so that's pretty much exactly what they gave us. That's where the graph goes. Where G has a horizontal tangent. Okay, if it has a horizontal tangent, that means it has a slope which is equal to 0. Okay, because a horizontal line has a slope of 0. So in order to find out if it has a slope of 0, isn't derivative the same thing as slope? The slope of G is the derivative of G. So where's that equal to 0? What values of x make the derivative equal to 0? Well, for the previous part, 5b, we stated that f is the same thing as the derivative of g. Okay? So if I want to know All right, if I want to know where the derivative of g is equal to 0, that's the same thing as asking, well, where's f equal to 0? What x values give me a y value of 0? I'm looking at the graph right now at this point here. That's negative 2x, y is 0. And at this point right here, when x is 2, y is 0. So there's two x values at negative 2 and positive 2. All right, so this happens at x equals negative 2 and positive 2. All right? But we're not done. We just answered this part where g has a horizontal tangent. But now we need to determine whether g has a local maximum, minimum, or neither at each of these values. So at negative 2 and positive 2, do I have a minimum? Do I have a maximum? This is for g. Or neither. All right. Time to erase again. Let's clear this out. And we're going to time to highlights because, you know, I don't want to forget. 2 points where g has a horizontal tangent or a slope of 0, right here and right here. And let us not forget that the graph of f is the derivative of g. That's going to be important. All right, so how do I know whether something has a minimum or maximum? If my slope, or in this case, my derivative of g, okay, goes from positive to negative, means it goes up, then down, then I have a maximum point. Okay? If it goes from negative to positive, it would go down, then up. That would mean I have a minimum. So my value of my derivative of g has to change from positive to negative or negative to positive at either one of these points to have a min or max. If it doesn't change, then it's neither. It does not have a min or max. So let's look at our graph again to the left here. And let's recall, okay, this is g prime of x. So my y value is the value of the derivative. And let's remember, basic rules for graphs. Anything that's above the x-axis has a positive y value. Okay, all these y values are positive. Okay, and anything below the x-axis has a negative y value. I mean, you can see right here, they're all negative below. So let's look at these points again right here. Do my y values change signs through these points? So here we go. Every part on this upper slope and this lower slope is a positive y value, isn't it? Any point I pick, there'll be positive y value. I hit 0, but then I don't go to negative. I stay above the x-axis, so these are still positive. So it doesn't change. It's a positive slope or positive derivative for g, goes to 0 at negative 2, then stays positive. So at negative 2, it's neither. Okay. And let's look at positive 2. Okay. Let's recall that as we're approaching positive 2, x equals positive 2, from the left side, I have positive values. Okay. Then it's a 0 right here. But then it goes down to negative. Okay, so at x equals 2, it goes from positive values to negative values. Okay, and we just said if it goes from positive to negative, you got to have a max. So there's a max here at x equals 2. And they want us to justify. So we're going to just put a quick note or some sort of words that explains what we just discussed. Okay? So let's go. So at x equals negative 2, why is there neither a min or max? Well, let's go gray here. Because the sign, S-I-G-N, of g prime of x, or the derivative of g, does not change here. It's positive, and it stays positive. Or if you want to say here, it does not change as it goes through negative 2. That might be even more accurate. It does not change as it goes through x equals -2. Okay, and why is there a max at x equals 2? Because g prime of x is positive. I don't like writing words. I like doing this. G prime of x is greater than 0. Then, as it goes through x equals 2, g prime of x becomes less than 0. Okay, so the value or the sign of g prime of x goes from positive, which is greater than 0, to negative, which is less than 0, as it goes through x equals 2. So, I mean, I wrote them two different ways, and again, there are a million different ways that you can write that explanation or justification. In fact, I've had people on my videos comment and say, oh, or you could write it like this. And they put out this very finely written, detailed justification. And of course, my response is, yeah, you could. And that's incredibly accurate. It's 100% credit you'd get. Absolutely. There ain't no shame in being right, folks. There ain't no shame in it. And the last section or part of 5D. Find all values of x on the open interval from -6 to 3 for which the graph of g has a point of inflection. Explain your reasoning. This one has to be words. Okay, explain. All right, let's explain. Let's start by breaking down the problem. Point of inflection. That's where the second derivative, that only happens when the second derivative is equal to 0. And again, the signs, positive to negative or negative to positive, have to change. Okay, and it changes signs here, okay? So let's figure out where, okay, let's figure out where we have a point of inflection. All right. And just quick to recall, point of inflection is where you go from a happy face in your graph to a sad face. That would be positive to negative. Or a sad face to happy face. That would be negative to positive. All right. You might also be saying to yourself, well, G prime, okay, not only does it have to be 0, it can also be undefined. Okay, the second derivative, point of inflection happens where the second derivative is 0 or undefined, not just 0. Okay, so keep that in mind because that might come into play because I'm seeing a lot of corners and cusps. I'll explain in a moment. All right, so here we go. First of all, we have established in parts B and C that the derivative of G is f, okay? So this graph of f is the same thing as the graph of the derivative of G, all right? So, but I need the second derivative now. So if I take the derivative of G prime, that gives me the second derivative. But I also have to take the derivative of the other side, okay? So the derivative of G prime ends up being the first derivative of f of x. And for the sake of this problem, derivative is the same thing as the slope of f. And now you know why these corners and cusps are going to be important, okay? So we need to figure out where the second derivative of g, which is the same thing as the first derivative or slope of f, where is that either equal to 0 or it's undefined? All right? Now, slope, okay, slope, that looks like another cusp here, okay? So slope is not the actual y value. I'm actually looking at the slopes of the graph given to us here. So I see a couple spots. All right, I see a couple spots here. Here, that's a corner, so my slope is undefined. Here, that is a cusp, so my slope is undefined. right here, there's a horizontal tangent line, so my slope is 0. And it looks like right here, there's another sort of corner or cusp. So let's just, okay, so my slope is undefined here. Okay, my slope is undefined at -2. My slope is actually equal to 0 at x is 0, and then it's undefined at 2. So right now I'm going to say at x equals -4, at x equals -2, because they're undefined at 4, undefined at -2, at x equals 0, because the slope is actually equal to 0. Remember, okay? Remember, it's where it's 0 or undefined. It could be either one, okay? And then right at x equals 2, I have another undefined slope, a corner or cusp. So, but a point of inflection, not only should it equal 0, remember, it should change, okay? It should change signs. And I'm talking about the slope should change at these points, meaning it should go from a positive slope to a negative slope or vice versa, all right? So let me get rid of this. So right now, let's look at where x is -4, that first or the far left blue highlighted point. Okay, I'm going from a positive slope to a negative slope right there. Okay, so that's a point of inflection. It actually changes. So I'm just going to say for -4, G double prime, okay, goes from positive to negative right there. Okay, that's good. So let's look at the second from the left blue dot, -2. Okay, I'm going negative. It's a decreasing slope, but then it pops back up and goes to positive. All right, so okay, because G double prime goes from positive, or excuse me, negative to positive, negative to positive. All right, so that's a good one. Let's look at 0. Okay, at 0, I'm going from positive. I hit that horizontal slope, and then I go to negative. So it's the same thing as I wrote for -4. G double prime goes from positive to negative. And now let's look at x equals 2, that last dot, blue highlighted dot on the right side. You'll notice I'm going negative as I'm approaching it. I hit 2, and then I continue to go negative. Okay, that's not an inflection point. My second derivative does not change. It is negative. It hits x equals 2, then it continues to be negative. So guess what? This isn't one of our answers. Even though the slope at that point is undefined, okay, where the slope is 0 and undefined is the possibility where I can have points of inflections. To make sure it's a point of inflection, I need to check if the sign changes. And the sign does not change at x equals 2. All right, hey, we're done. I told you we didn't need a calculator. Keep that in your back pocket. No, it's actually kind of big. It's bigger than a cell phone. You put it in your back pocket, it's going to break when you sit down. And you know what? Even though it's not as expensive as a cell phone nowadays, what, $1,000? It's still about $100, $150. So don't break it. All right, we are done. I am going to throw up another video after this for problem number 6, and that will be the final question for the 2018 practice exam. And hey, you know what? Like the video, follow me. You got any questions, comments, concerns? You just want to say hi? You know, throw up a comment. I'll try and get back to you. I will see you later. Bye-bye.
Don't forget to subscribe and ring that bell.